So we'll do just a simple concept with the bridge. And we remember that what we do is a bridge allows us to go over something. We have supports. And we have some sort of ground cover or something that the supports are sitting on. And there's water or a ravine or something here. And what we want to do is get a human being so they can go across this without getting into it. And the structure that allows this to happen is the deck of the bridge, or the structural portion of the bridge. And the human being stands on this and generates weight that pushes down on this thing. And the main issue associated with the bridge is that the bridge has to have enough structural design that the human being that's on the bridge, or however many human beings that are on the bridge, they do not, or the car that's on the bridge, or whatever structure you've got on the bridge, does not generate enough downforce on the bridge that the bridge bends or breaks. And the design constraints that go into the creation of the bridge have to do with putting enough strength in this structure that it doesn't break or bend. And what we've discovered with the bridge element is that a problem of bridge elements is that as the bridge gets longer, the structural piece that holds the bridge up, this structural piece has to get longer also. And as it gets longer, since it's a solid structure, this increases its weight. And so you can certainly hold a bridge up with a completely solid piece of metal that is no holes in it and no spaces in it. And the main trouble point with this form of construction is that as the bridge gets longer, this structural element gets heavier. And since this structural element gets heavier, basically, in order to support its own weight, you have to put strength into it that's enough strength to hold up whatever load you want, but also enough strength to hold up the weight of the bridge parts themselves. So when it's a short bridge, it's this tall, and when it's a long bridge, it's this tall. And as it gets longer and longer, it will become so tall that it's unworkable. One of the things that was noticed when you take a piece of steel and it's got a load stress on it, where the piece of steel is supported, and you're pushing down on the steel, it very, very subtly begins to bend. And you can take a strain measuring item and look at the strain that's in the steel. And if you do, you'll find that the strain on the steel from it being pushed down has this quality to it. And this is just a feature of science and materials and the way things are put together. And what people began to realize was, if all of the strain of the load that you're putting on the bridge is being supported by this area right in here, the question that came up was, what is going on in these areas? And if you measure the strain in these areas, what they discovered was there is no strain in these areas. And someone said, well, why don't we just take these areas and remove them from the bridge because they're not holding up any weight, or at least they're not holding up very much weight. And what they discovered is it's somewhat difficult to draw, that you can make bridge elements where the piece of the metal that's holding the weight is kept in the bridge, but the piece of the metal that's not really holding up anything is not in the bridge. And if you look at these truss members, support the elements of the load conditions for the bridge without the need for any material to be in this area. And this area turns out to be just air. You can see right through it. If the air was blowing along, it can blow through this and keep going. And this structure of steel with the trusses in it has just as much strength as a completely solid piece of steel that was this big. And it has a whole lot. This has as much strength as this. But it has a whole lot less weight. And so the point that we're trying to make is that when we're going to do a construction style, we want to do our construction with this form of material and not with this form of material, because this is too heavy. Now, something that we can discuss is that if we have the tubular elements of the bridge, or the bridge support structure, and we're running truss members to give enhanced rigidity to the bridge, then as we look dead on to this structure, we can see the four tubes in this dead on view, and the trusses are basically going from one of the support members to the other support member. Those are your trusses. And it is a principle of materials that there's absolutely no reason in the world why these could not be given this shape. They're not quite as strong. But if you had curved truss members, they would still have the same support characteristics that they do if they were straight. And if you move these out to the corners, you can wind up with a structure where you have your support elements and you have your trusses basically describing this shape. And the reason that we're trying to draw this in this way is to bring to your attention that if you take a solid piece of steel and expand that solid piece of steel into a tubular structure, in essence, while this tubular structure has the same amount of weight, this tubular structure has the same amount of weight as this piece of solid steel. This tubular structure has enhanced rigidity because you've taken the steel in the very center of this thing and turned the steel in the center of it into the equivalent of little trusses running along the edges of this structure. And you made these little trusses infinitely wide so that the entire skin of the tubular steel is actually your truss. So it doesn't have the tubular steel doesn't have the traditional triangles in it of material that have been cut out of it, like you see with the square structures of rectangular trusses. But a tubular steel structure, even though this is all filled in, still represents a truss because it is a way of enhancing the rigidity of a piece of steel by changing the way that the steel is fabricated. All right, so what we've established so far is that a piece of solid, round tube steel can be expanded into a hollow piece of tubular steel. And that when we expand it out into a hollow piece of tubular steel, the diameter is increased. But the weight is not increased because it's the same amount of metal. And the actual rigidity of this structure to being deformed by a gravity or weight pressure on this steel, this expanded version of that same amount of steel has an enhanced rigidity against compressive stress or bending stress, because we have, in essence,